Hello everyone, we are live. Hello Sebastian, hello everyone listening to us. Say hello as always.
Hi,
I'm
Konrad.
super happy. Hi.
Hi,
I'm super.
everyone.
We are super happy that you are here because we have an awesome webinar for you prepared today by Sebastian mostly. So this is a webinar about CPU profiling, what it is, how does CPU profiling works underneath, some differences in various profiling methodologies, let's say, what tools you can use, and some examples of .NET related profiling. Right, Sebastian? This is the agenda for today.
Yes,
So
exactly.
a very brief and fast journey through the CPU profiling in .NET ecosystem. First, of organization of some things about organizational. That's hard word really. Things about today's webinars. First of all, it is all about. I mean, maybe in other words, there was a tweet that we have provided this week, and you could win free access to our diagnostics expert course if you provide an interesting story behind a diagnostic in .NET. There were some interesting stories being shared by you. We have selected because we said that we announced the winner during the webinar. So here is the announcement. Congratulations, Tony. We are selecting you as the winner of this contest. So we will contact you regarding the ticket to diagnostics expert course. And we are really sorry that you have bad image, bad binary signature exceptions regarding emitting callee instructions. So sorry for that, but you have a free ticket for our course. So at least something to be more happy about. And regarding diagnostics expert course, sorry, I'm not a salesperson, and as you will be able to find out very soon, so I will not be talking a lot about that, but I just need to mention that we have the very last hour of our pre-sale to this diagnostic expert course. So if you will find interesting the things that Sebastian is saying today, or if in general you are interested in diagnostics, this is the course for you. The last hour now with the lowered prices. Sebastian is an author of this course, and we have also an awesome mentors, 11 weeks, 4 experts, live sessions, a lot of knowledge about this topic. So if you are somehow related to .NET Diagnostics, simply look around at this page and maybe you will find it interesting. So once again, hello everyone, and I believe now after this set of announcements we can move to the presentation, because I know that Sebastian prepared a lot of knowledge to throw on us and some demos. So maybe now, as far as I think, it is good place and moment to give a control to Sebastian. And Sebastian, maybe before you start, maybe not everyone knows you, you can say a few words about you, few simply small introduction about you, and then proceed with the talk.
Okay, sure. Yeah, so my name is Sebastian Solnica, and I have, as Konrad mentioned, I'm the author of this course, and I have more than 10 years experience in both development, .NET development and DevOps. I worked in both those roles, and in all my jobs, actually, I had a lot of tasks when debugging and diagnostics was required, and so I learned some experience, and we actually had even meetups here in Warsaw, which were dedicated to Windows internals, and also we had the debugging.
I remember
debugging
them. It was mind-blowing.
yeah.
I never forget the talk from you when you were using WinDBG to debug kernel of the a virtual machine to show how the debugger is working internally in the operating system. That was
we had some really nerdy topics during those meetings. Yeah, and that one was actually I of course I needed to make this research, but it was a really interesting one, how
right.
the kernel supports the debugger, so which ports are open. But yeah, that's that's a topic for another maybe meeting. I had some experience in both development and a bit in system engineering. That's also the reason why I talked with .NETos that maybe we could have a course dedicated to diagnostics, which is often a topic which is left apart, but in my opinion, it's very important, and it's good to know which tools are available. And when you're a developer, it's really good to know which tools are available for you when you meet a problem and you need to diagnose it. So I hope that you will find our proposal good for your tasks, and
right.
I'm pretty sure that it will be. But
nevertheless, today's amount of knowledge is also mind-blowing, so
I hope you will enjoy it. Yeah.
Okay, I will hide myself because it is you and your talk, so I will be just in the background and observing the questions, because if I will just stay tuned, and if you will have any questions, do not hesitate to ask. Maybe I will interrupt Sebastian, it will be really strictly related to what is being talked currently, or we will gather the rest of the questions to the end when we will have a short Q&A. So the scene is yours. I'm hiding myself.
Okay, thanks, Konrad. So our today presentation is about, as Konrad said, CPU profiling inside out. So we will cover the subject of different types of profilers, but we will also I will also mention some related tools to profiling, and then we'll run 2 demos and perform some diagnostics, live diagnostics. So before we jump into the profilers, let's first maybe just a brief introduction to the code execution and one subject in particular, which is call stacks. Because, well, as you know, when you are using the profiler, call stacks are very important. We need those call stacks to be able to say which methods are problematic in our code. So before we dive into the profilers, let's have a look how call stacks really work internally. So the processor has a register, a special register on 32 architectures, it's EIP. On 64 bits architectures, it's RIP. And IP in this name of this registry is instruction pointer. And this name already describes a bit what this register is responsible for. So when the CPU executes code, this register will point to the address which is currently executed by the CPU. And with that knowledge, when we know the instruction pointer, we are able to match this instruction pointer with a module that contains it. Additionally, each thread in an operating system, when the operating system creates a thread, it also creates some stack space for it. The amount of this space differs, and we can also control it. Of course, there's a default one. It's a continuous space where our application puts the either the local variables or parameters, some of the parameters, and also the stack information about the stack frames. And I prepared a little diagram that shows how the call stack is decoded. So that's what we see here. That's let's assume that's the call stack window in the debugger. So the currently executing method is method number 3. Then which was called by method number 2, and at the bottom of the call stack we have a method main. So that's a managed call stack. And if we look at the current state, let's say that we are stopped at the debugger. So what is happening right now? At the moment when we were stopping the application, so when the debugger stopped the application, the CPU RIP the CPU RIP register had an address of this assembly instruction. So the instruction pointer was pointing to some offset in the method tree. Then there was the CPU, the thread that was currently executing on the CPU. Let's assume that it was thread number 1, and it had, as I said, it had a stack space. And in the stack space, it had some local variables, and then at some place in the stack, it has also the previous RBP. And RBP is also another register which as its name suggests, it's a base pointer, stack base pointer. It is not obligatory to use this register for as a base pointer on the stack, but many compilers and actually compilers, because just-in-time compiler is also a compiler, use this technique to construct the stack frames. So we have the previous RBP, so the previous frame. We have a link here to it. So that would be for the method 2, and method 2 return and the next row. So the next address will be the return address for our method 3, and the return address for the method 3 is method 2 plus some offset, because if the method 3 finishes, we will the CPU will pick this address, the return address, and go back to method 2 and execute the next instruction after the call to method 3. And for method 2, the return address would be main with some offset. So that's how the debugger deconstructs the stack frames. And as a small, just to add some interaction to that, I thought that maybe we can do a very short demo, and I have a call stack application, so we can see how we can observe that in a debugger. So let's run the debugger. And what's important for this demo to work, we need to be in the debug mode. Oh, I stopped it by chance. Okay, so we need to be in the debug mode, because otherwise the stack, when we have the release build enabled, the stack gets optimized, and for instance, the local variables will not be put into on the stack, but rather passed through the registers. So that's a little difference one of the differences between debug and release modes. So here we have a main method that calls a test method and passes 3 parameters to it. So let's have a look at the registers that we have here. And the registers, you can open this window in the debug menu, Windows and registers, and we have the instruction pointer. And if we check this assembly, we will see that the instruction pointer points to the moment to the instruction at which we are stopped in the debugger. Additionally, if I scroll up a bit, I will move to the beginning of the test method. And as you can see here, there are a bunch of instructions which are called a prologue of a method in assembly. And this prologue is quite of course, it differs between architectures, but when we are on the same architecture, it's often quite similar, because there are some requirements put on the code, on the compilers from the architecture design. So for instance, here we are pushing on the stack, we are pushing 3 registers and values of these registers, just because those registers can't be changed by a method. So when we are getting back to this from this method, those registers should have their values restored. Additionally, this sub-statement here it allocates some space for local variables on the stack. RSP is the stack pointer, so it points always to the top of the stack. And at the end, we are we are assigning the RSP value to RBP. So RBP becomes the top of the stack. So to get, as we saw on the slide, to get to the place when we are just here, let's say at the stack, so when the RSI registers and their values are, we'll copy the value of the RBP registry, so this one. I will copy it to the memory window, and I will add the value of this subtraction. So we will skip the shadow space here for local variables. And I will also arrange this window a little bit better so it will look like a stack. So it will be easier for us to check it. And as you can see, if you look at the addresses here, we can see that those here belong to these ranges. I would call them that way. So those are pointing to the stack. And for instance, this one will be the RBP, so the previous RBP, and it will point to the main method, because that was the method that called our method. But this one will be the address of the return address of our method. So if we go to this assembly and paste this address here, we will land at the moment after the call to our test method. So as you can see, that proves what I just showed on the slide. Additionally, as we are in the debug, we can see that the values of the variables are also on the stack. So it will be easier for the debugger to extract them. So A in hexadecimal is 10, which we passed in the test method. Then Boolean, as you can see, is casted to the integer, and it's passed. The true value is passed as 1. And here, if I copy this value and I move to another memory window and paste it here, we will see that after the object header, the .NET object header, and the a method table address, we have the value of our string. So that's the .NET object, and so that address belongs to the GC heap, and that's where our string variable is located. So let's stop this debugger, close this Visual Studio window, and move back to the presentation. So that was a small introduction to call stacks, and it's time to get back to our profilers. So now I will talk about different types of profilers, and we'll start with the basic one. So the sampling profiler. And as its name says, sampling means that we are collecting samples. And this diagram shows how this sampling works. Usually we collect an event, the tracing event, every millisecond. That's by default. We can change it, but the default is usually fine. So you can start with the default when you are configuring the profiler. And when we collect the event, when we collect the sample, we actually are collecting the instruction pointer value of the CPU. So quite often we use kernel for that. It's at least that the kernel has access to I mean, it's the most efficient way to use kernel to collect those instruction pointers. But as we will see in a moment, it's also possible to use user mode, but in that case, it works a little bit differently. So for sampling, as you can see, we collect let's assume that we started the trace at 0 millisecond, and every millisecond, every other millisecond, we will receive an event from the provider. So it could be a kernel provider. Let's assume that. And with this event, we will receive an instruction pointer, and with some help from other events that we need to collect, we can identify the method to which a given instruction pointer belongs. So for example, here on the 0 millisecond, we received a method 1. That's how we decoded this instruction address. Then at 1 millisecond, there was another process, maybe idle process. There was another process running on the CPU. And as we are profiling a specific application, so the orange one, I should have said that the orange here means that the moment from the beginning when the orange starts is the time that our application is running on the CPU. So that's the CPU time of the application. So for instance, here our method 1 runs from 0 millisecond to some moment, then it does not have CPU time, and then it gets back and executes method 2 and then method 3. So at 1 millisecond offset, we have another process running. So it was not our process and we were profiling this process. So let's say that our profiler skipped that event because it did not belong to our application. Then at 2 milliseconds, it was again our application running on the CPU. So although we are in the method 2, there was a method 3 currently executing. So we decoded method 3 as the point to which instruction pointer was pointing. And at 3 milliseconds, we had again another process. So the result would be that we collected 2 events for our application. The first one had method 1, and the second one had method 3. So for the CPU, for the sampling profiler, the sampling profiler will tell us that 50% of the samples were on the method 1 and 50% on the method 3. So even now you can see that it's not really accurate because we are not seeing the method 2, what that was executing somewhere between the first and the third interval. However, when we collected the IP addresses, that's not enough to deconstruct the whole stack. So if we are interested in call stack, we also, to any provider that we use, we also need to add some additional flags. And those flags, if we enable those flags, they will force the provider to send us some additional events that are called stack walk events. And those events will contain the additional addresses that we will need to reconstruct the whole stack of the code that was executing. So with this picture in mind, let's move to let's discuss what are the benefits and the disadvantages of the sampling profiler. First of all, it has really low impact on the application performance when we use the kernel provider. And when we think of the sampling provider, it's one of the less invasive profiling that we have available. Additionally, when the application has a high CPU usage it is really accurate. I mean, we will see that in an example, but it's really safe to run the CPU profiler, sampling profiler, when we see that the application has high CPU usage. Additionally, the trace, as we are collecting by default, as we are collecting every 1 milliseconds, it's not really that often when it comes to the CPU time. So the trace file is relatively small compared to other types of tracing events that we will talk about in a moment. So what are the disadvantages? First of all, we can miss short-running methods. So if a method finishes between the 1 milliseconds intervals, we won't see it. And that also includes, we can't get the exact execution times of a method. So it's not like we will see, as we could see on the image, we won't find the method 2, for example, from which time it started at which time it ended. Same actually applies to the method 1, which was executing at the beginning. Additionally, and that's actually the biggest problem in the CPU profiling, is that it won't work for hangs or slow runs. So if we see an application which is running slowly or has some weights in it and hangs, CPU profiling is not the best choice because we won't get events for those moments when the application does not consume the CPU power, which means that we unless we are very lucky, we won't get the point when the application got the went into this hanging state, or when it started waiting for an event. Additionally, when we are using the user mode CPU profiling, it can impact the performance, because for kernel, in the kernel it's a bit different when the stacks are collected, because when the kernel collects the stacks, the kernel owns the scheduler. So everything is happening on the kernel side. It can easily go into the scheduler schedule and collect the required events. For user mode profiler, so if we use the profiler from .NET framework, for instance, then it will require to freeze a thread to collect its state. And finally, if we are using the kernel provider, we require some additional permissions to collect the trace. It's not like every user can do that. So it's often either an administrator or we need to be in a special group or have some special capabilities. And how do we trace? How do we perform the CPU tracing? So sorry for the resolution, but we will use that profiler in a moment. It will be better. So in Visual Studio, we have the CPU usage checkbox. That's for the sampling profiler. And if we click the gear icon, we will have an option to choose how many samples we would like to collect. And as you can see, by default, there's a sample collected every 1 millisecond, but we can go up to 8,000 events per millisecond. So quite often, but it's often not really necessary. In Purview, there is also a checkbox, CPU samples, and it is selected by default. So usually when you open Purview and start collection, the CPU samples will be there. Then we have perf on Linux, and in .NET Runtime repository, we can find the perf collect scripts, which will allow us to collect the sampling events from the kernel. That's perf is using perf events from the kernel. So we will get, when we are using the perf collect script, we will get the sample events provided by the kernel provider. Before you run perf collect, have a look at its documentation, because you might require some dependencies. There is a special install command that will install them on most of the most popular Linux distributions. And finally, the .NET Trace tool has a special profile and also provider, and this one is the user mode profiler. So it's the .NET framework that sends us the sampling events, and so it can affect the performance of the application. So bear that in mind when you have an application that does a lot of CPU, takes a lot of CPU time, because when you run it, you might expect some problems with, you might expect some slowdown. And here we can see what's the provider that they have. So we have some sample profiler in .NET Core that we can use to collect the events. Let's maybe move to the next profiler, which is called a thread time profiler. In other words, it's called a wall clock time profiler. So what does it mean, clock time or wall clock time profiler? It means that it can measure it collects the events in a way that we are able to measure time, and not the CPU time, not some samples, but rather we are able to match the clock time, so the time that we can measure on our watch with the execution time of the application. So to be able to do that, it collects an event when the execution of the application starts or stops on the CPU. And this event, when an application gets time on the CPU, so in this case, that would be this moment here, it's named context switch. That's just because the CPU switches the context. So it switches the context from one thread to the other thread. So it could be a context switch to a thread of our application, so the orange one. And when we have the thread time profiling events enabled, then when our thread gets a time on the CPU, the profiler will get an event, and again we'll get the call stack for it. So we will be able to reconstruct the call stack when our thread started execution, and then we will be able to recollect the call stack when our thread stopped the execution. So when either the thread finished, the application finished, or the CPU changed the context to switched to another thread. So maybe in another application or another thread in our application. So we have those events, and as in our example, in this case, we will receive 4 events, and the first 2 events will be for method 1. The second the other 2 events will be for method 2. And as I said, with those, as we receive the exact moment when the context switch happened, we are able to measure the time from one event to another. Of course, it might get more complicated. The example is very easy because it could be method 3 here. So that's that. But the point is that we are able to tell how much time passed from the time when we got time on the CPU till the moment when we when the context changed. And one more thing that I would like to add here is that the minimum amount of time that a thread gets on the CPU is called thread quantum, and it's not defined. I mean, it can change, and it changes dynamically based on the clock resolution of the CPU. Additionally, for desktop systems, this thread quantum is much smaller than for the server systems. It's just because the server system is usually prepared for background processes, so the processes have the background processes have higher priority, and we want them to run longer on the CPU, so they will perform more operations that they need to do. So, for instance, serve requests. But on the desktop machines, we have the desktop systems must be very responsive. So it's quite important to have the thread quantum short, so so the processor is able to switch constantly between different threads. For instance, for the UI applications, so they seem for us as users of those systems, they seem to be responsive. And so what are the benefits of using the thread time profiling? First of all, it has also a low impact on the application performance. Here we are measuring context switches, so there's no other way as to use kernel to get the events for us. And this type of tracing profiling is great for diagnosing waits and hangs, because as you can imagine, when the thread is waiting for something, the context will switch to another thread unless it's busy waiting. But assuming that we are waiting for some event, then the operating system is smart enough to get the CPU time to another thread, which at some point will yield and will make our waiting thread alive. So we'll be able to tell, okay, our thread got, by looking at the call stack, we'll be able to tell that another thread woke our thread because some, let's say, mutex, for example, was released. And additionally, it's quite pretty often we use thread time profiling with CPU profiling, and that's the best way to perform non-invasive profiling. So I would say that that's the most detailed way of profiling on the production, because we will get the context switches event, but additionally we'll get those sample events for every millisecond. So those two, when we merge them all together, we get pretty accurate view on the application of the application execution. What are then the disadvantages? First of all, we can miss, if we are not using sampling, we will miss methods which are executing between context switches. Even if you are using sampling, there is still a chance that we will miss them. And it's also quite, we can't be sure that a given method executed for a specific amount of time, because we won't be able to say that the method, when the context switch happens, it does not mean that the method finished. It will continue after the next context switch. So of course we will, the profiler can merge those events, but it's not like we'll be able to tell that the exact time when that the method took. Additionally, the bigger problem is that the trace file grows really fast when we are using thread time profiling, because even if you run a simple, just run it for a moment to see how many events a thread time profiler generates. So we need to be careful with that and keep that in mind. Maybe set the maximum, the limit on the file, or do not trace for too long if you are collecting the thread time events. And finally, the same remark as for the CPU profiler. When we are using the kernel provider, we need to have special permissions. And how to trace? So in Purview, we have the thread time checkbox, which enables those thread time events, and they will have when we have it checked, we will start to receive those events in our tracing session. On Linux, the perf collect script also has a special argument, thread time, and if we enable that, that's the same command as as you saw previously, but if we add this thread time, then we will also receive thread time events, so the events for context switches. So let's move to the next type of a profiler, which is an application profiler. And an application profiler is based on instrumentation. So when I say instrumentation, it means that we are modifying the code, that the application code. And the way how a managed application profiler works, if they are using the CLR profiling API, they are performing something called IL rewrites. So they are rewriting the IL code to create some hooks for the profiler. This way, as we can see on the image here, we can the profiler, the application profiler, can measure the exact time of a method, of the method that it decides to trace. It is still possible that profiler won't trace a given method. Maybe it has some heuristic, or maybe it has some code in it that decides that it should not trace this type of a method, or if the method is too short, maybe just don't trace it. But let's assume that in our example, we had a profiler which prepared those IL rewrites for all the methods in our application. So in that case, for our simple execution, we'll receive 6 events for each for the moment when the method starts and the moment when the method ends. So as you can see, we'll receive very exact times how long a given method took on the how long a given method ran. And that's the good thing about it is, as it's not using any sort of knowledge of context switches, the application switches, when the context switch happens, the profiler automatically is also not on the CPU, because the event is not generated. So we're receiving it is able to match the time when the method ends with some special code that's in the application. So what are the maybe first benefits? The benefits, as you could see, we can get the exact method execution times, and it could trace all the method calls that we want to. So we can even write our own profiler when we decide which methods we would like to trace. And the biggest disadvantage, and that's the one that actually makes this profiler probably not very suitable for production, is that it's very invasive because of those IL rewrites. So it impacts the application performance. We are injecting some code into the application, some additional code, which is later processed. So it could not be safe to modify an application on the production. I will always have something some risk. I will feel the risk when I would be using the application profiler in the production. And if we look at the tools which we can use, there are of course a lot of commercial ones, but if we are in Visual Studio, then there is this instrumentation checkbox that we can check. We can't have any other checkboxes selected if we are instrumenting an application. So, and we'll use that in a moment. So the next section is a short one just for related tools that we have apart from profilers that will tell us a little bit more about the state of our application. And I will start with task managers. And it's good to have a favorite one, because task managers will give you a lot of information about what is happening in your system. So if whether there are some interactions between processes, or which processes are taking CPU, how much memory they use, and all those sorts of information. So if you are using the default, for instance, task manager in Windows, you might be lacking a lot of information about the processes. So the one which is favorite for me is Process Hacker. Some administrators might not be happy about running it, maybe because there's hacker in its name. So it's maybe for some scenarios it might be safer to use Process Explorer, or maybe not safer, but it will be acceptable, because Process Explorer is signed, the driver of Process Explorer is signed by Microsoft, and it's a part of sysinternal suite, which was bought by Microsoft. So we can say that Microsoft owns Process Explorer. It's one of their applications. And on Linux, we have, of course, the HTOP and top. HTOP is the top with nice UI. And we also have PitStat, and PitStat is a really nice tool, because PitStat, we can enable PitStat to show output on every interval, and this output stays on the console, which is really cool, because we can get back in history and look what was changing on our CPU, so which processes were running. Not all other tools does not give us this snapshotting thing, so they are refreshing, and we lose the view of the moment in the history. And apart from task managers, we also have performance counters, and performance counters are quite good for observing the application. And when we in the past, when we were using only this old full .NET framework, we had the only choice we had were performance counters on Windows, and some of them were not very accurate. So it wasn't really sometimes. Well, not sometimes, but using some counters where it was not advisable. So we needed to choose other ways of measuring the performance. Right now we have the great .NET counters tool, and the .NET counters have a command monitor, which when you run it on a given process, it will show a view of different runtime counters. You can actually choose which one of them you would like to enable, and it will refresh on intervals to show the counter states. And another great feature about these .NET counters is that they are internally using the event pipes API, and it's fairly easy to add your own counters to your application. For instance, Entity Framework Core adds a Microsoft Entity Framework Core counter, which you can enable in the monitor command by using this command with these arguments. And when you enable that, you will see how many transactions were running, how many objects were cached, how many connections to the database were open. So pretty valuable information when you need to triage the application. So when you need to learn what's going on before you even start a profiler. So both the task manager and performance counter can tell you some insights about the execution before you even start tracing. And the last, I forget, Visual Studio also has an endpoint for .NET counters, so that's using the same technology under the hood, and we can see those counters also in Visual Studio, so there is a view for them. And we also have profilers, sorry, I misspelled here, based on custom events. So those are profilers which they are not really profilers, but we can add them to this group as they are listening for specific events, like, for instance, the start of a task, the end of a task, or of some specific activity. And based on those events, they show us some information. And in Visual Studio, for example, we have a .NET Async that I will show you in a moment. And then we have also the concurrency visualizers. Maybe some of you have played with those tools already. And in Purview, for example, we have a special parser for activities and for tasks. That is smart enough to group the traces that we collected into activities. So it can mark when a given activity started, when it ended, and then we have a nice, for instance, view for for a whole request in the application. And I think that's it for the slides. It's time to switch to demos. So I will
Awesome.
go to Visual Studio.
Waiting for the demos, praying for the demos goals. Especially for the Visual Studio ones.
Yeah.
A very short reminder, it is the last 15 minutes before we close the pre-sale of this course. So just as a information, if you are so focused on the talk that you may forget to buy the ticket. Okay, so good luck with the demos then. And also remember, you have all possibility now to ask the questions, because obviously we have a lot of knowledge, but if you have any question, do not hesitate to ask. We like answering questions, right?
Yeah, exactly. Ask questions and we will try to answer them. I hope we'll have
from
answers.
The speaker's perspective, even especially online speaker, it is so nice to have some questions, because it really means that some people are really there and they are listening and not sleeping. So it is even much more important than on site event, for example. Okay, I'm shutting up, and let's just continue.
No, but that was a very good remark. Exactly, because whenever you ask questions and when you are active in the chat, we can know that there is someone there listening. Exactly. So moving back to our first demo, that's a very simple application in which I would like to show you the instrumentation and the CPU sampling profiler. And in the last webinar, I also used it briefly when we looked how the instrumentation works. It's the first example is a very simple one. So we have a file hasher. We are computing a hash for a file. So that's SHA-256 that we calculate on a given file, and we would use this application to check, for example, if our download does not miss some bytes, or some bytes are incorrect. So, and I have a big file here, the test.db, which has more than 800 megabytes that I will calculate the hash of this file. And we'll start with the instrumentation profiler. So I will uncheck all the other boxes and the instrumentations becomes available. In the previous webinar, if you saw it, if not, have a look at it. We were looking at how the instrumentation profiler works internally. So which API is being used. There are some environment variables that needs to be set. And I also mentioned that if you are using this instrumentation profiler, you need to have the debugging information set to full. So that's something that you need to remember. And that's quite unfortunate because the default one is portable. So I hope that in the future releases of Visual Studio, we won't need to change this debugging information. Additionally, we have some options here. For instance, we can exclude small functions. I don't want to do that because my function could be considered small. So that's when you have a lot of noise in the instrumentation. It's quite it's good to have a look at the documentation and check all those various options. So without any further delay, let's maybe start our application under the profiler. So that's the file hash application. It will calculate the file hash and it should create a report for us. So that's the profiler started the application. It is now calculating the file hash, and and the application finished. And we got the report. And before we dive into this report, let's maybe run also the CPU profiler. So instrumentation, I will select it, and I will pick CPU usage. And as you remember, there is this options dialog when we can define how many samples we would like to collect. Let's say that for our examples, 1000 per second is fine, because we could see that the application lasted for at least a few seconds, so we should be fine here. So let's run the profiler, and again, let's run the application. It will calculate the hash. Let it give it a moment. Okay, now we can see that the application is working. Previously, it disappeared mysteriously. So we have the CPU report being generated, and here we have the instrumentation report. So the summary is quite useful. Usually, in our very simple example, with this nice fire icon here, we can see immediately where our problem lies. That's actually in our code is this file hash program compute hash. It might not be that obvious in your applications, so you might need to go to call tree and then dive into the call stacks. But if we are here, we can also see that we have the number of calls of a given method, and that's when you remember the slide when I was talking about the application profiler. Here we have more than 200,000 calls to the transform block cryptography API that we are calling in when we compute the hash. But also we see that almost more than 99% of the execution time of the application was spent in this method. So that's our culprit in this situation. But if we switch to the CPU profiler, the one thing that you should notice is that here that we do not have any gaps. So it means that when we were collecting the events, the sampling events for our application, the application had time on the CPU. We can see that it's not 100%. It's the reason for that is first that I have several cores, and this application is one thread. It's running on one thread, so it will never occupy all the cores of the CPU. But additionally, maybe it even did not fill one core of the CPU. However, it was running constantly. That's an important thing here, that we had the application was taking the CPU time, so it should be wise to use the CPU profiler. I mean, we should be safe using it. Additionally, always check the number of collected samples. So here we have more than 5,000 samples, which means that at least we covered 5 seconds. Or maybe not necessary, because there could be multiple cores, but in our case, when there's only one thread executing, it means that we have more than 5 seconds covered by this trace. So when we look at the whole time of this trace, it means that most of it was covered by our profiling events. And okay, we see here a lot of call stacks that look a bit native. So let's that's interesting, because we have the hide native code selected, but we could, if we do not recognize these methods, we could start from hiding the external code, just to see what maybe we can by just simply looking at our application, so at our compute hash. In our case, it's the compute hash method. We always will see also one additional external call that's just after the internal call. I don't know how to call it differently. So the call in our application is compute hash. I hope you can see that. And but the big fire is here. So in the append hash data, which later which is used, which is a method from the crypto API. And if we click on this method, we'll land in another views that are available. So we also see the source code if we have the symbols which are matching. So we have the call tree view, and here we can expand and go further into the call stack. So if I enabled the external calls, then I would be able to also go through them. So if we expect if this view with the external code hidden, does not tell us much, it's worth to enable it and check it again. But if I go back to this report, one important also information that the report reveals is also the categories. We can see what from which different categories the CPU, the sampling events we got. So for instance, here we have that, we see that most of the events were coming from the security category, which is probably connected somehow with the cryptographic APIs that we are using. Some of them we have from kernel, and then we have file system, and also we have just-in-time compilation. So that was our very simple example to show you. Okay, one more thing is that when you remember that in this in the application profiler we had an information that the compute hash took about 99%. So that's we can always trust the instrumentation profiler because that's the most exact one. But if you look here, we see that it says that. Oh, actually, the number of samples was much higher. Sorry, I should show you this one. So the one on the top of the call tree, not the one. So we see that we had almost 7 seconds covered, so the whole trace. But the compute hash here in the CPU profiler report, we see that it has 97%. So it's quite similar. So that's why we can say that it's pretty safe when we see high CPU usage in an application to use the CPU sampling profiler. It should show us accurate data. Okay, I'll show this. Sorry, I'll close this example and we'll move to a little bit more complex one. Oh, we're going out of time, so it's probably some more minutes required. But we have again the application is quite simple. It's an application that
we don't have something like running out of time.
We have. People might went sleep.
Oh, okay, sleep. Maybe from this perspective.
We have an application that is showing, that is listing, I call it employees. So there's just a list of people that will show on a view. As you can see, it's we have the I think it's called Razor pages, right? So we have some page model here that with a limit of 5,000 people that we will retrieve from a person table from a database when there is no search string set. And when the search string is set, then we will look for last names which start with a search string. So quite straightforward, and we just list them here in a loop. So I will prepare the trace for our example. So, and for our example, we'll use this .NET async that I mentioned in the slides. I will keep the CPU usage. One reason to keep the CPU usage is that if you disable it and collect any other trace, you will lose the timeline. So this nice view over the events tables that shows you the CPU time and also shows you the execution time of your application. So it's always I think that it's recommended to just have this checkbox selected for the CPU usage. And I will also enable event viewer. And if you recall from the previous webinar, I was talking about the Microsoft Extensions logging provider. And this Microsoft Extensions logging provider has a view in Visual Studio. In the previous webinar, I told you that I prefer to use per for those events. In a moment, we will see why. But if we use, actually, this view becomes more and more useful in Visual Studio. So I hope that in the near future, we'll be able to switch to Visual Studio completely. But right now, we need to just select the logging, and I'm interested only in formatted messages here. We can choose collect events or collect events with stacks. I actually want only to collect events. And I want to do that only because I want to do the diagnostics in a little bit, in a little harder way. By default, we will probably set the trace here to add either information, or we will have some another logger data store where we log information about the requests being executed by ASP.NET. I won't do that. Let's try to analyze the application without the logs. So it will be a little bit harder. Let's assume that's a misconfigured application where we do not have good logs for it. So we'll collect with those three enabled. I will start the application, and to make things interesting, let's say that we got a report about 2 bugs in the application. The first one is the homepage loads very slowly, and the second one is that when we search for something, it also is pretty slow. So let's start the application and have a look at how it performs. So that's the homepage loading, and as you can see, we do not have much information in the log because we are on the warning level. So we saw that the main page took some time to load it, and let's search for one last name. And again, as you can see, the search takes some time. So that's another issue that we have. And I need to stop the application. That's a bit unfortunate. And I think that's a bug in .NET Async right now. I think it's still in preview, because when I was using this stop profiling button in Visual Studio, I were not getting any events. So I had no events in this view, and that was pretty problematic because, well, I had the CPU usage, I had those other events, but it looked that Visual Studio was missing some random, I guess that it was missing some random ETW events for the tasks providers, so the ones that Async is based on. And but if we have those events here, this view is really great, and I hope that they will add new features to it with time. I will maybe hide the solution so we can the whole view, so we can see the whole view. What it shows us, first we can see the activity. It is lacking some information because, well, I would like to see the query string here, but I hope it will come. We can see that in purview, for example, but it's still great that we can see the total time of a given activity. So, for example, here I have the first request that's problematic. It took about almost 8 seconds. And here's the other one, so the search one, when we were searching for the last name. And it took almost 5 seconds. So we see that those, especially on local hosts, that shouldn't be that long, right? The extracting 5,000 rows from a database shouldn't be that hard. So we will diagnose both those problems. But so maybe let's start with the second one. And before we do that, let's select on the timeline the moment when this request started and till it ended. So we have the 17 seconds, and that's a bit tedious how you need to do that, because you need to wait for the tooltip to show up and tell you at which point you are on the timeline. So it would be, I hope we'll have a better way to do that. But once we selected it, we can see that the time over the timeline is changing when I move the mouse. So we can select the 5 seconds. So that would be this exact moment of this request. I hope the events will get filtered. Yeah, I can see this request here, and now I can focus on it. So I can expand the tree here, and by looking at the total time, I can go deep into those rows which has the total time, high total time, because those are the interesting ones. And as you can see, the .NET Async is sort of thread time. No, maybe not thread time. That's a bad word for that. But the clock time profiling. So we can measure the time when a given task was executing, and that's really cool because well, in those async applications that we have, we know that there are a lot of continuations on task, and it's sometimes hard to find which method caused the problem. And here, for example, the stack was automatically expanded as those were the continuations and the task waiting for other tasks. And at the bottom, we can see that there is entity framework core storage relational command execute reader async that took almost 4.5 milliseconds. So that means that we could be pretty sure that's the problem with a database. So our database query was taking too much time. So in the next step, we will have a look at the database. But before we do that, or maybe let's have a look at the database. So I have the testdb, which is on a local SQL server. And if I run the sp-help command, we can have a brief look at this table. We can see there's first name, last name, and it has the primary key on the ID column. And that's basically it. We do not have any indexes on this table. So we can assume that, okay, we do not have index on the last name, so let's add this index and on the person table. So I will create not clustered index, create index X person, then last name on person, and then last name. So I will run this command, and the table is pretty big, so I will leave it here. And in the meantime, let's have a look at the CPU usage. And here we have a bit of a problem, because where we do not see that the application was taking CPU time. So that means that in almost 5 seconds, right? We had almost 5 seconds time selected here, and we can see if we go to the tree view. So if I go to open details and then I pick tree view, at the top we can see that we have only 200 samples. So it means that we covered only 200 milliseconds of this whole 5,000 millisecond period. So and here we probably had multiple threads involved, so we can assume that it should be even more than 5,000. So that means that what we are getting from the CPU profiler is not that should warn us that we probably shouldn't use the CPU profiler to diagnose this problem. And if we even enable the show external code, we will see that we will land in some mysterious place like thread pool worker queue dispatch, which takes, according to this report, it takes 70% of our time, which is, as you know, when we looked in the other trace, in the wall clock time trace in .NET Async, it's not true. So so our index finished, and so our search should be fast now, right? So let's filter for another string, and it's still snow. Oh, sorry, our application is not running, so it's not surprising. I will start it, but I already told you that our fix probably won't work. So let's just have a look that it's still not working. I mean, it's working, but it's still slow. So why it's still slow? We miss one thing when we were performing our diagnostics. I mean, we jumped to a conclusion before we finished the identify step, so the first step of diagnostics. And in the identify step, we should also check the query which was causing the problem. So when we know that it's a database, we also should check what query is being executed by our code. So if we go to events now, and just a brief introduction to this view, we do not have the problem with it. My biggest problem with it is that we do not have many filters available. So we can filter by the provider, and that's what I'm going to do. I will only select the Microsoft extensions logging, so the one that we were using. Oh, sorry, I need to apply. And I will leave the event filter as it is, or maybe I will filter it to a formatted message only, because those are the logs of the application, so something that interests me now. And I will also remove the provider name. It's also event name. All our events. I can't remove that. Okay, never mind. And here I will expand the column and I will look for the entity framework events. So I will look for first events which has that event entity framework created. And as you remember, in .NET Trace and in Purview, we had a, I guess, much better view how to access the information, the formatted message, and the arguments which are serialized into this formatted message. So that is why I prefer to use Purview to collect those events. But if someone wants to stay in Visual Studio, I just wanted to show you that it's possible. So here we have a compiling query expression, so not probably the one, but here we have generated query execution expression. So maybe that's the right one. If I copy it here, yeah, we can see what's our query. So the one that's being executed on the or maybe I can stay in Notepad, but I will just remove the rest here. And so the code that caused this that created from which this query was compiled is this one. So context person where, and we are looking for last name which starts with search string. And if we look at the SQL which is generated, I know it's not about profiling, but it's just a brief digression. So we can see that actually entity framework did what we asked for. So it substring the last name for the length of the search string, and then it checked whether this search string equals the search string that we provided as an argument. But that if we looked at the query plan, we'll see that causes an index scan, or maybe even the index scan, because we need to go through all the search strings. So what I would prefer to see is something like that. So where last name p dot last name and here our search string which will contain a percent at the end. So fortunately we can easily replace that logic here with so I will maybe copy this line and comment it out, the previous one, and here I will replace that with ef functions like, and our expression is last name, and our search string, I will simply just add a percent to the end of it. So we could do some sanitization, but it's not that important at that moment. So so if I build the application, and maybe stop this one, if I build it and run it, and go again to our main page, we can also see that the main page is still not fixed, so it's taking time to load these 10,000 people. But if we search, we can see that we get an immediate answer. So finally, of course, we should also check the query again if it's what we want, but I can tell you that it is. And we also see that the query, to string, because there were more people matched. So, but moving back to our main page, we see that the solution that we had, and also from the code, we can see that it did not help in the first case. So let's go back to our trace and give it some more examination. So we will get to async activities again. I will clear this selection, and I will select the previous request that we had collected, that we have collected. So that was the first request that, as I remember, took almost 8 seconds, so a very long one. And this time I will again do the same steps. So I will select the time span. It's tricky, and then 8 seconds from here, roughly 8. So if I'm above 8, it will be fine. Okay, and let's give Visual Studio some time to reload the views. Okay, so here the situation is a bit different, because we can see that there is some CPU power involved in this whole time. And if we can again go into this into the collected traces, but what we can only say from the .NET Async screen is that well, first of all, there are some not really telling us much task process data rights, and it's in the HTTP to output, so that's probably the whole task of our request. So not really something that we can build hypothesis on. And here we have also a very short time. So, but we have from looking on the timeline and the CPU usage, we can see that okay, the application was doing something, so it was probably not waiting on something else. Maybe one thread was waiting, but we do not see, at least on the task side, because of course it could be waiting on something else. But in the task view, we don't really see. I forget one more point here. We can expand this view and then go deeper into the request here. But as we can see, that the last, actually we can go deeper, but at some point we'll see that the call, that would be the last method. No, also we have this one. Yeah, we can, as with the async traces, it always really we can go deeper and deeper. So in this case, actually the call to the database seemed to be also quite, it took some time in this request, but it was the whole, sorry, I'm looking at the end time. Sorry, not the right column. Okay, so now we can see that it was 1 second of this, of the whole time of the request. So here we have the last, yeah, I always fool myself when I take the end time column as the total time, and then I'm fooled and I'm looking for events that do not exist. So here we can see that there was a jump from 6 seconds to 1.4 seconds. So this 4.5 second went somewhere, and that's something that we need to investigate, because that was from some resource invoker. So that's not really something that rings any bells in my head, at least. And when we go deeper here, we still could find this entity framework task that was making this toList async, and we can see that it took about 1.0 second of this request. So that was, we still need to learn what was the rest of the time. When was the rest of the time spent in this request? As we have this CPU usage like that, we can go to the CPU usage report, as we can learn something from it. And there are some hot paths again here, but maybe we'll leave the show external code enabled here. The interesting point here is that we can see that the just-in-time compiler events, there are lots of them. So that's something that maybe we should be worried about. What are those coming from? And if I open the details, I had it open, sorry. So I have the call tree. If I try to go deeper into this call tree, I will land in a very mysterious land, and I see that the call stacks, maybe I will show this, close this report, and I will try to reopen it. And that's something something I need to warn you about. If you see hexes after the DLL, it might mean that you hit a bug in the profiler. And it happened to me on several occasions. And so I will tell you in a moment how to fix that. But let's go to the functions view, maybe I will be able to show you what I want to show you. I still see that we have the ASP.NET call stack collectly resolved, so there is still hope. So instead of going through a call tree and going down the async call stack, which can be really hard to get, I mean, at some point you will get to those important methods, but as you know, the call stacks, even when we have an exception in the async awaitable code, the call stack tends to be a really long one, and it's hard to find yourself in it, and especially when you are in the profiler. So we will try a different approach. We'll try to find methods with the high number of samples collected inside this method. So when we, which means that the body of this method was taking a lot of time of the CPU. And here we can see that all other methods has really low those CPU bodies, and they probably were calling one of those methods. So there is some native code that we would need to enable the native code to diagnose. So, and it's taking, it has a lot of samples, but that might be misleading. So before you try with the native code, don't try first with the managed code. And so we have the one interesting managed code here, which has the highest number of samples collected in its body, and it's more than 2,000. So this method executed for more than 2.0 seconds. So let's have a look who called this method, and for that we can go into this caller callee view, which is pretty nice, and it's worth exploring when you find a method like this one in our case. And here we can pick, usually it's safe to pick the method, the parent method, the calling function, which has the highest percentage in this view. So let's go that way, and let's use this way of going up till we hit the call stack that we know. So here I will go some. We are in. If I scroll over, move my mouse over this button again, I will see the tooltip. That's a bit unfortunate that maybe on a better resolution I needed to switch the resolution so you could view this better. But in the tooltip we can see the whole name of a method. So we are in some MVC, view features, model, explorer, get model. Let's go further. We are in some template builder. Then we are in HTML helper, generate display method. Then we that there's an interesting ill stop. So there is something probably being created dynamically here. And we have a HTML helper display extension, display4. That should ring a bell for people who are playing with, who are working with ASP.NET Core. So let's go a bit further, and here we go. Here we are in our call stack. So here there is a function in our code that's calling the other function. And if you look into the namespace, it's people pages index. So if you are using Razor pages, you will know that this type of convention, so this underscore index this type of names is generated from the views, and they are coming from another assembly that was automatically compiled. So our views were compiled into this assembly. So knowing that, we know that's the index view, and we also know that we should look for some display4 method. So let's go back to the source code of our application, which is for the view. And here we can look for where we are using display4. Here we have display name 4, but here we have display4. And that's something interesting because we are here iterating through that should be persons, because that's a list of of people. And we are displaying a first name. We want to learn about the attributes of, so we want to use the attributes over the first name property. but I haven't diagnosed it fully. But my wild guess is that if we are creating a closure here, we are forcing. I mean, the expression here can't be cached, and that's the reason why it's being rebuilt for each item in this loop. And a very simple fix for that would be to simply, as those are strings, we could do something like that. And item last name, and comment out this code. So we will simply put out the strings, and I will rebuild it and see if it helps in our case. So I will rerun it. I hope it will, because it was working. So if I refresh the page, we can see that the page load was faster. If you would like to use those display attributes, I did a small experiment to prove that the closure is the problem here, and we could do something like this, although I wouldn't give my hand for that, but I think it should be working. So we can create a function that will take both the models. So I think it will be index model. Then we will take another argument. It will be the person, so our person, and then the result would be string. So I will call it first name, and we can use it will be a function. So it will take let's say the first, so the first argument will be model, the other will be person, and we will return a string. So we use here the display 4, and here we'll have model, which is model, and then we'll take first name and simply return it. And here, okay, I made a mistake. I think, I might need to consult my file. Let's give me, I will have a look. What should be what I'm missing here? Okay, that was the display name for, okay. Oh, okay. I won't spend time on this. It's just what I tried to do here is that if we extract this expression above, so if we build a function that won't be rebuilt here, but we simply call this function using the arguments that we'll pass the item and the model, then I think that the display 4 returns not string but something else. And that was the reason. Okay, no more time on this. Never mind. So, but if you build the expression, the function somewhere above, and then reuse it here, we should be probably safe. So we should be able to not generate this expression reboot. At least I think so. We need as an exercise you might try it. But this example was taken from ASP.NET Core documentation. So I think that it might be quite popular. I mean, if you have more items than if the number of items in the loop is higher, then you probably will notice this bug. But if not, then well, you might not see it till the moment when the number of people in the list gets bigger. Okay, so that's it for it. So those are all the demos. I took almost 1.5 hour more, but I hope you liked the demos and the presentation. So
and they
now
worked. When they worked.
Yeah, fortunately. I will add one thing about this profiler. So if at any moment you see hexes after the DLL name, and that unfortunately happens when you rerun the profiler, the workaround for that, for the current version of Visual Studio, is to go to the folder of a method, remove the cache of the Visual Studio, and restart Visual Studio, and the call stack will be there again. I'm not sure what's the problem there, because I have the symbols. I checked in the debugger that the symbols are loaded correctly. So it's not the problem with the PDB files, but rather something that the profiler is doing. So remember to remove the VS file and the .vs folder and and restart Visual Studio.
If something doesn't work, you need to restart it.
Yeah.
You can always diagnose why it is not working, right?
Exactly. That would be a nice diagnostics with Visual Studio.
Debugging Visual Studio debugger or profiler. That's the level of of things. Awesome. So thank you, Sebastian. It was very, very nice.
Thank you. Thank you for being here.
It was very nice journey through various profiling possibilities with some examples, live examples. So it's always nice to have it. And my sound is very low. I don't know why. That's very strange. It shouldn't be. But fortunately, I was not speaking a lot today, so. And okay, so now we have the time for the very last questions, because there was no questions during the talk. So maybe now, the very last minute, I need to scream to the microphone. Okay. No
questions.
problem.
We are waiting for questions.
Yes, we are waiting for questions. So I'm screaming for questions. And if we don't have any, then we will end in a minute. So in the meantime, we close the diagnostic expert course, because it was promised to be closed at 8. And now we will start to learn diagnostics, right? And I'm shocked you didn't use
Run perfect.
Yes.
I planned to, but I really ran out of time. Also, I should have shown different ways of collecting the events, but it's really hard to put all that information in 1 hour. So
it's only 1 hour and a half.
Yeah.
But still only 1 hour and a half. So definitely. Okay, so any kudos, because I'm just closing the call in a minute, so in a few seconds. So any congratulations to Sebastian if you like the talk. Thank you, Sebastian. We will see for sure during other online events, or maybe at least eventually in some on-site events. So
at some point, hopefully.
Yes, at some point, at some day, eventually we will. So thank you everyone for watching us. Thank you for being. Thank you for not asking questions. And we will see somewhere. Thank you very much. And
Thank
have
you.
a nice day.
Thank you.
Bye.
Bye.